In the last session, we have discussed about the issues faced in commutation and how to mitigate those issues. Now we'll be basically taking up how to now we'll basically take up the actual internal generated voltage equation of a DC machine. So now as we know that the voltage induced in one conductor E induced is equal to VBL. Fine. So this is almost just a repeat. We have done most of this. So voltage induced one conductor is equal to VBL. One conductor means actually one side of a coil, and so the voltage induced in this is VBL. Therefore, but we now know that if there are Z conductors in the DC machine, Z armature conductors, these are armature conductors we are talking about. If there are Z conductors in the armature and A number of parallel paths, then in one parallel path number of conductors will be Z divided by A. Fine. Z are the total number of conductors of the armature, and A number of parallel paths in the DC machine, in the armature of the DC machine are A. So we understand this, that A will be equal to 2 for a wave winding and A will be equal to the number of poles for a lap winding. So therefore in one parallel path the number of conductors will be equal to Z divided by A. So since number of conductors in one parallel path will be Z divided by A, E induced in the parallel path will be equal to Z divided by A into VBL. Since E across all the parallel paths is same, so this will be actually the armature EMF as well, that will be available to the that will be actually available, considering there are no losses. This will be the voltage that will be available at the once the that will be actually generated in the DC generator, Z divided by A into VBL. We have also modified this equation, and we defined we can define V equal to R omega and B, that is the magnetic field in strength, equal to flux divided by the area under the pole. Right? Now, area under pole, what will area under pole be equal to? If 2 pi RL is the area of the entire circumference of this cylinder, fine, where R is the radius of this armature, L is the length of this armature, fine. So since this is a cylindrical structure, L is the length, R is the radius, 2 pi RL will be the area, total area, but we are talking about area under one pole, so this will be equal to 2 pi RL divided by P. So if P were equal to 2, then AP would have been equal to pi RL, that we have seen earlier. But if P is equal to 4, then area under the pole will only be equal to 2 pi RL divided by 4. Fine. So therefore B is equal to phi divided by 2 pi RL divided by P. Fine. So P goes phi P divided by 2 pi RL will be B. V is equal to R omega. Substituting both these two values, one this and this equation in this equation, EA will be equal to Z divided by A. Instead of B you have R omega, and instead of B you have 2 pi R L. Instead of B you have phi P divided by 2 pi R L into L. Fine. So L and L goes, R and R goes. So you are left with Z divided by A, 2 A pi phi P and omega. Fine. ZP divided by 2 pi A into phi into omega. So we can basically note from this that ZP and A for any particular machine, ZP and A will be constant. Once you have DC machine given to you, these will be constant, but phi and omega can change depending upon the other parameters in the system. So we can take ZP divided by 2 pi A equal to K phi omega. Fine, where K is basically ZP divided by 2 pi A. So this is our induced EMF equation. EA is equal to K phi omega in a generator, in a DC generator. So you can see from here EA is proportional to K. So for a particular machine, this will be constant more or like, and there are very few machines where you can basically modify the conductors or the poles of the machine. Fine, but EA is proportional to phi and EA is proportional to omega. Therefore, if your flux increases, your internal induced EMF in the generator, DC generator, will increase, as well as if your speed of rotation, that is the mechanical energy basically, that will increase. Again, your induced voltage, generator voltage, will be increased. Fine. So EA is proportional to both flux as well as the speed of rotation in case of a DC generator. We can also modify this equation 1, and in terms of, we know omega is in radians per second, we can convert it into RPM, 2 pi by multiplying it with RPM by 2 pi by 60, you will get actually radians per second. So actually if you are obtaining RPM, then you need to multiply radians per second by 60 by 2 pi. Fine. So this is your equation that relates basically omega, that's in radians per second, and speed, that's actually in, again this is your, both are your representation of speed. One is in radians per second, another one is in RPM. So instead of omega you can write 2 pi by 60 into n. Fine. So EA in this case will be what? K into 2 pi by 60. 2 pi by 60 is again a constant term, so if we multiply this with K, this will become K dash phi n. Fine. So where K dash is now what? K earlier was ZP divided by 2 pi A. Now what did we do? We multiplied it with 2 pi by 60. So 2 pi and 2 pi cancels out. This is ZP divided by 60A. Fine. So K dash is ZP divided by 60A, or you can also write it here like this, ZP phi n by 60A. So these are your equations that you can basically use for calculating induced EMF, induced voltage in a DC generator. You can make use of any of these equations that are actually depending upon what values you have been given. EA is equal to K phi omega, or EA is equal to K dash phi n. Fine. Or in the expanded form it is ZP phi Zn P by 60A, or it's phi Zn omega by 2 pi A. Fine. So this is your induced EMF voltage. Similarly, induced torque equation. Let's see induced torque equation in a DC generator. Now as far as induced torque goes, we have also derived the value of torque in one conductor, that's equal to R I L B. This was torque in one conductor. where I is basically your current flowing in one conductor. Now if IA is the total armature current, I mean to say if there are P number of parallel paths, fine, there is some conductor here in which current is flowing I conductor. That means actually in this whole path the current that is flowing is I conductor. I is the current that's actually available at this point. So if I is the current flowing through the armature current, is the total armature current, then what is the relationship between I conductor and IA? I conductor is equal to IA divided by A, because we know that the current will be split in the in the parallel paths equally. So torque torque in one conductor can be represented by R I A by A L B. Now since there are Z number of conductors in the DC machine, total torque that will be induced will be equal to Z R I A L B divided by A. Fine. So this will be induced torque will be the summation of individual torques of all the conductors that's actually acting upon all the conductors, and that means simply torque induced will be equal to Z R I A B L divided by A. Fine. Again we have found out the equation of B. B is equal to 5P divided by 2 pi RL. So substituting that here, we get induced torque is equal to Z R I A divided by A L, and into B. B is 5P divided by 2 pi RL. Fine. So L and L goes, R and R goes. So torque induced is equal to Z phi P divided by 2 pi A Z P 2 pi A phi into IA. Now I have written this in this fashion particularly because ZP divided by 2 pi A is what we know already from the previously what we have defined. K is ZP divided by 2 pi A. This is the same constant of constant that is actually at both the in the both equations. K phi IA. Fine. E induced is K phi omega. Torque induced is K phi IA. E induced we have also derived in terms of speed as K dash phi n. Fine. K dash is something different. So this is your equation of torque induced, and that you can use. Again, you can see K torque is proportional to flux, and the induced torque is also proportional to armature current. Fine. So this is actually the torque that will be induced in the DC machine. This is not the actual applied torque to the DC machine. So having derived these equations, now let's do some numericals on this, and we have our question states a duplex lap wound armature. You have a duplex lap wound armature. It's used in a 6-pole DC machine, and with 6 brush sets. Okay, you have 6 brush sets as well, each spanning 2 commutator segments. Fine. So each of these brushes spanning 2 commutator segments. There are 72 coils on the armature. There are 72 coils on the armature. 72 coils on the armature, each containing 12 turns. Each is containing 12 turns each. Fine. The flux per pole in the machine is 0.039 Webers. Flux per pole. This is for 5P. .039 Weber, and the machine spins at 400 RPM and is given to you 400 RPM. So you have been asked how many current paths in this machine. Fine, this is one part, and B, you have been asked to derive the induced voltage. What is induced voltage? EA. Fine. So before we start with this question, there's a term here that we have not discussed so far, that is duplex. You'll come across two terms, simplex and duplex. So what you have in case of simplex lap winding, A is equal to P. So that means basically the number of parallel paths will be equal to the number of poles. While as in case of duplex lap winding, A is equal to 2P. That means there will be actually twice the number of compared to simplex lap winding, there will be twice the number of parallel paths in a duplex lap winding. Fine. So the windings are basically placed in such a fashion in the slots that in such a case the parallel paths become twice the number of simplex lap winding. So this is a duplex case. So now let's find out the number of current paths. First of all, we know the number of current paths for a lap wound is equal to P, but for a duplex case now it will be equal to 2P. So number of parallel paths or number of current paths A is equal to 2P in this case, not equal to P. It's P A is equal to P for the simplex one. And since P is equal to 6, that means 2 into 6 equal, that means A is equal to 12. There are 12 number of parallel paths in this machine. Now second, you have to find out the induced EMF in this case. You have to find out EA, and since you have been given in terms of, you have been given N, that's RPMs, so you'll be using this formula, phi ZNP divided by 60A. Fine. So phi has been given to you. Phi has been given to you 0.039 Webers, and we have been given N, the speed of this machine, 400 RPMs. We have been given P equal to 6. A we have just now calculated is equal to 12. Z we know is equal to 2 into C into number of turns. Fine. And C, 2 into number of coils into number of turns. Number of coils were given to us. There are 72 coils, each having 12 turns. So 2 into 72 into 12. So this is equal to 1728 conductors. Therefore, EA is equal to phi, that's 0.039, into Z, that's 1728, into N is 400, into P, it's 6, divided by 60 into 12. So you can calculate this and you should be getting 224.6 volts. Fine. So in this question, the term that we had not introduced previously was duplex lap wound. So simplex lap wound is simply where the number of parallel paths is equal to P. In a duplex lap wound case, the number of parallel paths will be twice, that means 2P. And rest of the things, these equations have been already derived. So using those equations, we can find out that our total induced voltage in this case is 224.6 volts. So let's do another numerical. So a 12-pole DC generator, you have a 12-pole DC generator. It has a simplex wave wound, armature containing 144 coils of 10 turns each. Resistance of each turn is 0.011 ohms. Its flux per pole is flux has been given to us. Fi is 0.05 Webers, and N is 200 RPMs, and its turning speed is 200 RPMs. So A, number of parallel paths, we have to find out. B, induced armature voltage in this machine, that means EA we have to find out. C, what is the effective armature resistance of this machine? Effective armature resistance of the machine. And D, is if a 1 kilo ohm resistor is connected to the terminals of this generator what is the resulting induced counter torque on the shaft. Fine. So these things we have to find out. Firstly, the number of parallel paths of this machine. Now we know for a wave wound machine, the number of parallel paths is always equal to 2. Since this is a wave wound machine, A will be equal to 2, and number 2B, you have to find out the induced voltage in this. EA, you have to find out phi Z N P divided by 60 A. Phi has been given to you, it's 0.05 Webers. Z, you have to find out Z, the total number of conductors, 2NC. 2 into number of coils is 144 into number of turns, that's 10. Fine. Into P, the poles of this machine, 12, into N, that is 200 RPMs. Fine. Divided by 60A. 60 into A is the number of parallel paths, that's 2. So this is your total induced armature EMF, and if you calculate this will come out to be 2880 volts. Fine. C is important here. Now we have to find out the total effective armature resistance of this machine. So we have to find out the total effective armature resistance. What we have been given is resistance of each turn is 0.011 ohms. Number of conductors is written by Z. Z is equal to 2 Cn. Fine. 2 into C was given to us 144 into N, that's 10. So that means 2880 conductors. Fine. So these are the total number of conductors. Now total number of conductors in one path, Z per path, will be equal to 2880 divided by number of parallel paths, in this case that's 2. So you have 1440 conductors. If you have 1440 conductors, that means you will be having 720 turns. What this basically means is, this is your coil. This is a conductor here. This is a conductor here. This here represents a turn. So for every 2 conductors you have 1 turn. So if you have 1440 conductors, you will be having 720 turns in this machine. Fine. In one parallel path. So in one parallel path, the resistance now will be, resistance per path is equal to 720 into 0.011. Since we have been given the resistance of each turn, so that's why we are finding in terms of turns. We found our number of turns, multiplied by 0.011. So this will be equal to 7.92 ohms. Now this is resistance per path. There are 2 paths, they are in parallel, so effective resistance will be 7.92 into 7.92 divided by 7.92 plus 7.92, as you do in case of a parallel, how you basically solve 2 parallel resistances. In short, this is 7.92 divided by 2, that's equal to 3.96 ohms. So this will be the total effective resistance of the armature of this DC machine. Now what you have been given is, in D part, you are adding a 1000 ohm load to the terminals of this generator, and effective armature in this case will be actually, since compared to 1000 ohms, the armature resistance 3.96 is very small, so we'll actually ignore that. So therefore current in the armature current will be equal to 2880, that's actually the induced EMF 2880 that we have just calculated, divided by 1000, the applied load. So armature EMF is equal to 2.88 amperes. So this is our armature current in this machine. Therefore now torque will be equal to therefore the torque will now be equal to phi z p I a by 2 pi a. Fine. Phi is given to us 0.05. Z is 2880. Fine. So your Z as well as voltage in this case are coming out to be equal to 2880 into P. The number of poles is 12 divided by into IA, that is 2.88 divided by 2 into pi into A, that's the number of polar paths, that's 2 in this case. So this will come out to be equal to 396 Newton meter. So this will be the induced torque or the counter torque that will be produced in this DC generator. So since this is a DC generator, it will not be an induced torque, it will be a counter torque. We refer to it as counter torque. So these are about these are some numericals that we have done today. Now the last part of this of today's lecture, we will be doing the power flow study in case of a DC machine. Power flow and losses in a DC machine. So as we know, the generators basically consume the mechanical power and convert it into electrical power, and the motors basically do the reverse of this. That this conversion is not exactly 100%. The input power that the mechanical energy or the electrical energy is supplying, and the output power that will be available to us will not be equal. There will be losses in this machine, and because of this loss, the output power will always be less than the input power in the machine. So if P in is your input power and P out is your output power, fine. You can define the efficiency of this machine as P out divided by P in into 100%. Fine. So these are your this is your efficiency of this machine. Now, what are these losses that are what are the different types of losses we see in a DC machine? So there are actually 5 losses. You have the copper loss, you have the brush loss, you have core loss, you have mechanical losses, and fifthly you have the stray losses. First, copper loss, as I have already discussed this previously also, these are simply the I square R losses in the machine. So you have the field winding as well as the armature winding. So both these windings, the field winding will have its own resistance RF, the armature winding will have its own resistance RA. So current is flowing through both these paths. If IF is the current flowing through here, IA is the current flowing through here. Therefore, the field winding copper loss will be equal to IF square into RF. These are simply the heat, the losses that are dissipated in the form of heat through these windings. And similarly, in the armature, PA copper loss will be equal to IA square RA. Fine. Then you have the brush losses. The brush losses are derived as PBD equal to VBD into IA. So what are these losses? These are simply the losses owing to the drop in voltage at the contact terminals of the brushes. Fine. So you basically have the brushes in contact with the commutator segments. Fine. So because of this contact, there will be some effective resistance at this point that will contribute to some voltage drop. This voltage drop is more or less constant, and that's why we are deriving the equation in terms of V and I, not in terms of I and R. Fine. So these are brush losses are the losses owing to the drop in voltage at the contact of the brushes of the machine. VBD is mostly constant, and more or less VBD is taken as equal to 2 volts approximately in most of the machines. Unless otherwise specified, you can take VBD equal to 2 volts. You will be knowing the armature current, so you can calculate the brush losses in this machine. Then you have thirdly the core losses. The core losses, as again we have discussed this, these are the hysteresis and eddy current losses. Hysteresis losses are because of the non-realignment of the domains of the magnetic material that actually result in the hysteresis loop. So you can basically see that extra amount of energy that you need to spend for reversal of current is basically a loss in the machine. And similarly, the eddy current losses because of the induced voltage in the magnetic surfaces as well, in case of armature or in the pole faces. Eddy current will begin to flow through the armature as well. The structure, the solid structure of the armature, that will be actually a loss. These are basically the magnetic losses in the machine. The brush current, the brush losses and the copper losses, they are purely electrical, but core losses, these are owing to the magnetic nature of the material. Hysteresis and eddy current losses are obtained, so therefore they will be actually proportional to the frequency of the armature current. Fine. Then we have the mechanical losses. Mechanical losses, they are of two types. One is the friction loss and second is the windage loss. These are simply friction between the mechanical parts, like the bearings you have. That will lead to loss of some energy, and windage losses is because of the friction between the armature and actually all the moving parts, the rotor and the rotor and air. Fine. So there will be friction between the rotor and the air that will also contribute to losses. So despite all these losses that we have defined, we have found out there are some losses that are undefined in the machine, and there's still the mismatch between the input power and the output power, and therefore these losses are characterized as stray losses. They are undefined losses in the machine and referred to as miscellaneous losses. So we can basically now draw the power flow diagram of a DC machine. So for a DC generator, your input power is basically the mechanical power. That means it will be applied torque into omega. Fine. So applied torque basically means, say for example, your gushing water is moving the turbines of the DC generator. Fine. So that pressure, that actually force is that causes the turbine to rotate is known as the applied torque of this machine. That is not the induced torque of the machine. So the first losses in this machine that are seen are the stray losses. The next losses you will see in this machine will be the mechanical losses, that's the friction and the windage losses, because the rotary part comes first in the DC generator. Then you will see the core losses, and finally you have the copper losses. Core losses are also known as iron losses. So you will finally get the output voltage. You can also calculate the output power in terms of the terminal voltage that's obtained and the load current that's flowing. At this point you will be actually getting the converted power. That means the power at this stage is converted from mechanical energy into electrical energy, and this is the power that you can calculate through EA, IA, or torque induced into omega m. Fine. EA is the induced voltage in the machine, but at the output terminals you will be getting VT. So VT and EA basically will not be equal. There is voltage drop in this machine because of the resistance of the windings of the machine. And IA, the armature current, again depending upon the type of machine, you will be seeing IA, you will be having a relationship between IA and IL of the machine. So accordingly, this power, the converted power at this stage, is not equal to the output power that's obtained at this stage because of the losses owing to the copper losses in the machine. And in case of DC motor, this power flow diagram will be reversed. Your input power will be in this case VT IL. Fine. So first of all you'll be having the copper losses, that's I square R losses. Then you will be having the core losses, you will be having the mechanical losses, and finally the stray losses. And your output power will be equal to torque applied into omega m. At this point you'll be getting converted power EA IA, that's also given by torque induced into omega m. Fine. Torque induced is something that we can derive using our equation, and torque applied is actually what we are, in case of DC generator, is actually the source of energy that's applying the torque. In case of DC motor, it will be what the motor is basically applying to the mechanical load that's connected with the system. So this completes our one portion of DC machines, wherein we have identified the basic principle of operation of DC machines, the equations, the different types of losses, and the power flow diagram. Now we need to study different types of DC machines and their characteristics. Different types of DC machines, I mean by that we need to now study the series DC machines, the shunt DC machines, the separate